to introduce some results on the nonlinear logarithmic Schrodinger equations. Okay, this is a joint work with Professor Alves. I think everyone, maybe you all know Professor Alves. Okay, by the way, I'm Chao Ji. I'm from China. I work for East China University of Science and Technology in Shanghai. Where I hope when the virus passed, maybe you can visit Shanghai. It's a beautiful city. Okay. First of all, let me get started with the background of our problem. The logarithmic Schrodinger equation given by like this. The special part is this logarithmic nonlinear term. And this equation appears a lot of physical applications, for example, quantum mechanics, quantum optics, and Bose-Einstein condensation. My research interest is to looking for the standing wave solution, like this kind of solution. In order to look for this kind of solution, it's equivalent to looking for the solution of the semilinear elliptic equation. This equation. This is a semilinear elliptic equation. Okay. Here I'll show you some difficulties when we deal with this equation. Here I assume here is a constant. I assume it omega is bigger than -1. It's not important just for simplicity. Later I'll show you we can weaken this assumption. Okay, the functional G associated with this equation is this functional. Okay, here let's pay attention to this number. Here is a 1. Why do we have to add 1? Because the derivative of this function has 2 terms, so we should add 1 here. Okay, let's see this integral again. Okay, sorry. Let's see this function again. If this function is divided by u square, when u goes to 0, its limit is -infinity. If this function is divided by u, the absolute value of u to the power q is between 0 and 2. 0 and 2. For example, u to the power 1. When u goes to 0, its limit is 0. So if the absolute value of u is small and near 0, so this function can be controlled by c times the absolute value of u to the power alpha. Alpha is between 0 and 2. It's very important for our problem. We know the Sobolev embedding h1 into h1 of Rn into Lq of Rn. Q is bigger than or equal to 2. So if function u is small on an unbounded domain, so this functional could be -infinity. Maybe I can say more. because if alpha is between 0 and 2, the absolute value of u to the power alpha is bigger than the absolute value of u to square. So this functional could be for some u, this functional could be minus infinity. So this functional could be infinity, like this. This is very important for our problem. Okay, here I can show you, I can give you an example. U is a smooth function, satisfies this. Here n is a dimension. So if we can, from this example, we can see ux is small and near 0 on an unbounded domain. Okay. What's the point? What's the point if this functional is not safe one? What kind of difficulty do we have to face? Because if the functional is C1, we can construct a pseudo gradient field, which is local ellipsis. So we can construct a deformation. This is very important for classical critical point theory. It's very important. But this functional is not C1. We cannot do that kind of thing. So we cannot use the classical critical point theory. Okay, because of the same reason, inherent manifold is not C1, and not closed. Here I can show you. This is a inherent manifold. Inherent manifold is a subset of H1 of Rn, which satisfies this equality. More precisely, you belong to this side, d of g minus 0. What's the dg? dg is a subset of H1 of Rn. Satisfied g of u is finite. So because functional g is not C1, so we can, because of that reason, we can know this is not C1. Because we choose this side, not this side, so we know inherent manifold is not closed. Okay. If inherent manifold is not C1, so we cannot use Eckland variational principle. Later I'll show you. Okay. The nonlinear term does not satisfy the A Ambrosity-Ramanovich condition. For our problem, the nonlinear term is u times log u square plus u because as I said before, because u square times log u square, the derivative of that the function has two terms. So our problem, so nonlinear term is okay, u times log u square plus u. Okay, I think you all know AR condition. So you can try it directly. It's a standard. Okay. AR condition is important to verify the boundedness of PS sequence. But our nonlinear term does not satisfy this condition. How to prove the boundedness of PS sequence? We use the following logarithmic Sobolev inequality. This equality. This equality is not enough. We also need this equality. 2 times g of un minus g prime of un times un equals this. This is L2 norm. square. Okay, this is important. So if un is a PI sequence, so 2 times g of un equals this. It's very easy. It's very easy. It's a standard. We can choose a to be small enough here. Here for all a is bigger than 0. So we can choose a to be small enough such that this term minus this term could be bigger than and bigger than or equal to this term. Is a standard. Okay, we can move this part into here. Okay, let's pay attention to this function, this term. This is L2 norm. Here is H1 norm. So we can use this integral is less than or equal to d plus little n of 1 times this H1 norm. So if we use this inequality, we can get this inequality. So here we can choose R is between 1 and 2. So we can get the boundedness of PS sequence for the functional G. It's a normal way to prove this. Later I'll show you. In our problem, we cannot use for our problem. We don't have this equality. Later I'll show you. Okay. Now I can let me show you some properties of our problem. Maybe I can say I'll show you some properties of logarithmic Schrodinger equation. For any s belong to R, this inequality holds. Why? As I said before, if the absolute value of s is small, so this function can be controlled by c times the absolute value of s to the power alpha. Alpha is between 0 and 1, because here is s, not s squared. So of course, if, because s is small and near 0, the absolute value of s to the power alpha is between 0 to 1. It's less or equal to 1. So we can get this. If we choose the s, choose s is big, so we have this. This is less than or equal to this part, c times this it. Okay, I don't know if you understand me. Okay. This is a subcritical growth condition. Subcritical growth condition. So if omega is the bounded domain with a smooth boundary, G, the functional G is C1 in H1 of omega. We in our research we use these properties. We use this property sometime. Okay. As at the beginning, I assume this number omega is bigger than -1. As I said before, this assumption is not important, just for simplicity. Okay, now I can explain why. For example, omega is -100, -1000, -10,000. Maybe it's a indefinite problem, but it's not, because we can substitute u with lambda v. Here lambda is positive in the following equation. We can get this. In fact, we can get lambda here, lambda times this function equals lambda times this function. So because lambda is positive, so we can cancel lambda and get this equation. Okay. If we choose lambda to be small enough, so this number will be bigger enough. So this number will be bigger than -1. So they are not the indefinite problem for the logarithmic Schrodinger equation. Okay. But here I will say some more. If here is not a number, constant, if here is a potential, here is a function, for example, Vx. If the potential Vx is unbounded below, this method doesn't work. If the potential is unbounded below, this substitution doesn't work. So this kind of problem is meaningful. Some guys has solved this problem. Later I'll show you. Okay. Now let's review some known results. Some important results. In this paper, Davignia, Schrodinger. In this paper, they consider the functional G on the radial subspace as merely lower semi-continuous. Effect, they use a long-smooth critical point theory. They obtained the infinitely many solutions, which is radial. Every solution is radial. They get. Okay. Moreover, for this equation, here is a constant. They prove this equation has a unique C2 classical solution, which is a radial non-generator. Okay. Because of this this result, people can construct a positive people can construct a solution by Lyapunov-Schmidt reduction method. For example, in this paper, his name is Luo Pen Niu. In this paper, they consider the singularly perturbation problem. In this paper, the potential Vx has L different critical points, which is non-generate, which are non-generate. So they can. It's very important assumption. Okay. In this paper, Schrodinger and Stuking consider logarithmic Schrodinger equation on an unrestricted space H1 of Rn, not subspace. On unrestricted space H1 of Rn, they decomposed the functional G into the sum of a C1 functional and a convex lower semi-continuous function. Motivated by this paper, Stuking and I consider a logarithmic Schrodinger equation with asymptotic conditions for the potential. More precisely, when the potential is coercive, we obtained the infinitely many solutions. In the case of a bounded potential, we obtained a ground state solution. Okay. In this celebrated paper, this is Professor Zhiqiang Wang. I think maybe everyone knows this professor. They use this is a maybe I should. This is a power law. This is a nonlinear scalar field equation. Nonlinear scalar field equation. Here, it has a power law. Power growth. Okay. Okay. By this kind of scaling, we can get this equation. Okay. Let's pay attention to this part. Not you. Not include you. Just this part. Okay. We can see this function as a to the x. Here a is the absolute value of u, is a constant. Here x is p minus 2. Okay. If p goes to 2, this limit is log the absolute value of u. This actually here is let me show you a simple example. A to the power a to the x. Its derivative at x equals 0 is ln a. So you can get ax. The derivative of a to the x is a to the x times ln a if x equals 0. Okay, like this. Okay. Because the function of this equation corresponding to is J1, so we can use the classical critical point theory. So in this paper, they use the ground state solution of this equation, convergent to the ground state solution of this equation as p goes to 2. Okay, by the rescaling like this, they can get the ground state solution of this equation. So, okay, this is a very good method. Okay, in this paper, using the idea of this paper, they consider the side changing solution. Okay, or nodal solution. Okay. Finally, I have to mention this paper. This is Zhang Chenxiang, Zhang Xu. In this paper, they consider a logarithmic Schrodinger equation with the potential unbounded below. As I said before, here, if here is replace this number by a function Vx, if Vx is unbounded below, this method doesn't work. So they consider in this paper, they consider that case. Okay. Because my research background, I'm familiar with Schrodinger and Stucking's method. So I motivated by their method, Professor Alves and I did some work. So I can show you some more preliminary results. For this function, the difficulty appears when the absolute value of s is small. So we choose f2 of s equals 0 when this holds. So we don't have any difficulty. But f2 of s minus f1 of s equals but we cannot delete this part. So we assume f1 of s equals this part when this holds. Okay. Oh, here. Oh, why did we and the delta and this? Why do we write this? Because we want to this function is convex and is non-negative, so we can use subdivisional. So because this kind of form, we can show f1 is convex even and which is non-negative. So because of this, the integral of f1 over Rn is lower semi-continuous. Okay. We also need this inequality. Why? Because of even the functional g satisfies the PS equals. For example, g of un goes to c, g prime of un goes to 0, and this sequence un is bounded and un goes to u strongly in h1 of Rn. But because the functional g is not continuous, so gu maybe does not equals c. But because it's not continuous, but because of this inequality and other something, we can prove gu equals c. Okay, this is a subcritical growth. It's a good term. It's good term. Okay, we can rewrite the functional g as g of u equals phi of u plus psi of u. This is a good functional. This is a bad, not good functional. This functional is it's convex, even it's non-negative. So this functional is lower semi-continuous. Okay. Why Schrodinger and Stuking wanted to rewrite the functional g as this kind of form? Because they can use the result from this paper. In this paper, Stuking considered a minimax theory for lower semi-continuous for functional. So this is the side partial g of u equals this side. Okay, it's called the differential of g at u. For our problem, it's lucky. If g of u is finite, this side is not empty. And there is only one element. So maybe if you read some paper related to logarithmic Schrodinger equation, they also write g prime of u. In fact, it's not C1, but they just write g prime of u in form. Okay. Because okay. For if g of u is finite, it means this, and z belongs to this side. It means z has a compact support. So this equality is meaningful because z has a compact support. As I said before, G is a C1 in H1 of Rn. So this is meaningful. Okay, if you read some paper, maybe the authors wrote G prime of U x on Z equals 0 for every z belongs to this side. So u is a critical point. U is a critical point of functional g. It's not exactly right. In fact, we should see more. Here we must see this. G prime of U is densely defined linear operator. If this norm is finite, we can extend. So then G prime of U may be extended to a bounded linear operator in E, and is an element of E prime. So if G prime of U x on z equals 0 for every z belongs to this side, so must be extended to a bounded operator in E, which is 0 in E prime. So U is a critical point theory. So U is a critical point of the functional G. Okay. I have cited this. This. Okay. Now let's talk about our goal. Our goal under different types of potentials. Here are types of potentials. Our goal is to study the existence, multiplicity, and the concentration of a positive solution to this problem, to a logarithmic Schrodinger equation in the semi-classical setting. Okay, this is important. Okay. Okay. The first result is a multiplicity result about when the potential satisfies a global assumption. More precisely, V is a continuous function such that this limit holds, and there exist L points Z1, Z2 up to ZL in Rn, with Z1 equals 0 such that 1 equals V of Zi equals minimum V of X over Rn. Here I is here. Okay. No, okay, sorry. Okay. Okay. The first result is suppose that V satisfies V1 and V2, then there is epsilon star is bigger than 0, such that this problem has at least L positive solution in H1 of Rn for all epsilon is between 0 and epsilon star. Okay. Our result is motivated by this paper with the Chao Ji. Okay, in here they assumed that there exist L points Z1, Z2 up to ZL in Rn such that this holds. Here is the maximum, not minimum, because our potential is here. In this equation, the potential is here, so we have different. So here is a maximum. Our problem is it's minimum. Okay. The main difference is the function of this equation corresponding to is C1. In this paper, they consider problem on the inherent manifold. In fact, effect. Maybe I can show you. Here is an inherent manifold. Inherent manifold. They construct. Okay, I'll show. Maybe okay. Here Zi is this point. These points. This is my problem for proof, but I can show. Maybe I also can use these notations for Chao's paper. Okay. Because they are at different points, so we can choose root zero small enough such that these sides are mutually disjoint. These sides are mutually disjoint. Here Q is this function. This function is a mass concentration function. If you read some paper, maybe it's we usually use this function. We call it a mass concentration function. It's continuous in H1 of Rn. So because these sides are mutually disjoint, and this functional is continuous, so we can get L mutually disjoint bounded open side on the inherent manifold. So they consider L local minimizer, L different local minimizer on the inherent manifold. So the next step is we have to show the solution on the inherent manifold master the solution of the original problem. So they use Eckland's variational principle. But for our problem, we cannot use that. So we consider the multi solution for the problem on a ball firstly. So this is inherent manifold is C1. So we can use the method of this paper. Okay. We can get L different solutions for the problem on a ball. Second, we can let R goes to infinity. It's easy to show for example, we can get a local minimizer is a UR. Here is the UR. It's easy to show UR is a bounded sequence when R goes to infinity. It's easy. So UR goes weak has a weak convergence. For example, it's U. It's also easy to prove U is a solution of original problem. It's very easy, but we don't know if U is non-trivial. Maybe U is 0, so it's not meaningful. So we will use this name to prove U is a non-trivial solution. Okay. I just show the main idea. Here is a limiting equation. It's in the Schrodinger and the Pietro-Davinia's paper. We know this equation has a ground state solution which concentrate on a bounded domain. If U is a solution on a ball, if U is a solution on a ball, lies in inherent manifold, and this inequality holds. So this U has a similar shape with the ground state solution of this equation. So this U also concentrate on a bounded domain. Actually, we want to prove the weak limit is non-trivial. We will use concentration compactness principle due to PL Lyons. So we have to prove compactness holds. The reason is I said before. I said it just. Okay. So okay. Finally, we have finally the third step is UR goes to weak convergence. The U is non-trivial, but we don't know LU if LU are different, because we want to get L different solution. So we cannot prove UR strongly convergent U in H1 of Rn. So we adapted the function. We adapted the definition of the mass concentration function. This function. Normally, normally, here is not G. We add a G, is a radial positive continuous function such that this holds. So we can prove we can get a L different solution. Yeah, so we made some adaptation, okay, for the definition of mass concentration function. Okay. Oh, the second result is the existence and concentration of the logarithmic Schrodinger equation when the potential satisfies a local assumption due to Pino and Felmer. More precisely, V is a continuous function, and this holds infimum of V of x over Rn equals V1. There exists an open and bounded site lambda satisfying infimum of V of x over lambda is less than minimum of V of x over partial lambda. Okay. If you our result is, suppose that V satisfies this V1 and V2, then it exists epsilon 0 is bigger than 0, such that for any epsilon is between 0 and epsilon 0, problem P epsilon has a positive V epsilon. Moreover, if eta epsilon is a global maximum point of V epsilon, we have this limit. Okay. Our problem, our result is motivated by this paper. I guess you guys all know this paper. Pino and Felmer is very famous paper. They considered this equation. In order to study this equation, the biggest difficulty is lack of compactness, because Sobolev embedding from H1 of Rn into L2 of Rn. Q is between 2 and 2 star is not compact. So that's a big question. They assume f of c equals little o of c as c goes to 0. This assumption means that f has a subcritical growth as c goes to infinity. This is AR condition. This assumption normally we will use inherent manifold. Okay. in order to overcome the lackness of compactness, so they used panelization method in order to overcome that difficulty. So, but for our problem, the nonlinear term is u times the log u squared plus u. This function does not satisfy this assumption. You can compute it directly. T times log t squared plus t is divided by t. As t goes to 0, this limit is minus infinity. So how to use this method? How to use the panelization method? Okay. In order to research this equation, normally we need to make a change of variable. For logarithmic Schrodinger equation, it's same. Okay. Let's recall that f2 of s is this. Okay, here is consider as c goes to 0, as c is very small. F has a superlinear. F is a superlinear. Let's take a look at this function. Okay, f2 of s equals 0 when the absolute value of s is small. Of course, the derivative of f2 prime is also equals 0. Okay, 0 is divided by non-zero equals 0. So this limit is also equals 0. So maybe we can try to see f2 prime as a nonlinear term. Maybe we can try it. Okay, we can try to compute it. f2 prime of s over s is non-decreasing for s is positive, because when s is small, this number is 0, so is equal 0. So it's non-decreasing. Okay, if s is bigger than delta, we have this. We also can get this limit. It's very easy to verify. Okay, so we can use the panelization method due to the Pino and Felmer. This is a standard. This is very standard. We can consider this function as a nonlinear term. Okay. So we will consider this modified problem. This problem called the functional of this problem corresponding to is this. Okay, it's easy to construct a mounting path for this functional. It's easy. But the second step is to verify the boundedness of this functional. We can get a P sequence. It's very easy. But how to prove the boundedness of P sequence of this functional? As I said before, we need to use logarithmic Sobolev inequality and this equality. If we don't do modification, we have this equality. But for this functional, for this modified functional, we don't have this. So in order to prove the boundedness of P sequence, we need more dedicated estimates and use the following logarithmic interpolation inequality. It's hard to prove this. The second The second difficulty is we also need to use inherent manifold for u. Actually, for some special u, not for some special u, we need to prove there exists a unique T such that Tu belongs to inherent manifold. For this functional, it's very easy. But here, if we made a modification for this functional, it's very hard for u. It's hard to prove if there exists T, a unique T such that Tu belongs to inherent manifold. Okay. The first step is construct a mounting path, so we can get a PS sequence. When we prove the boundedness of the PS sequence, so we can get the PS condition holds. So we can get a solution for the modified problem. The second step is to prove the solution of the modified problem is a solution of the original problem. So we need to do some L infinity estimation. In fact, we need to do multiple iteration. It's a normal scale. Okay, I'll show you. I'll come back. Oh, sorry. I will do multiple iteration. We can get this inequality. In fact, we should say this L infinity norm is small enough for n uniformly. If for every n, this is small. If R is big enough, this is small enough. It's okay. It's trivial. But for n uniformly, for every n uniformly, it's hard. So we need a compact result. Phi n of x has a convergent subsequence in H1 of Rn. So this phi n has a convergent subsequence in L2 star of Rn. So in order to prove this result, we need this lemma. Here un is a critical point of the modified functional I epsilon n. Okay. So we can prove then if this holds, then there exists the subsequence yn such that phi n of x equals un of x plus yn. It's a translation has a convergent subsequence in H1 of Rn. Okay. In order to prove this lemma, we need an important estimate. C epsilon n goes to C0. So C0. This energy goes to the ground state energy of the limiting equation. This is a functional of the limiting equation corresponding to. As I said, actually, I mentioned the main idea of the proof of this lemma. It's okay. I'll show you. Because the ground state solution of the limiting equation is concentrate on a bounded domain. So if C epsilon n goes to C0, so this solution has a similar shape with the ground state solution of limit equation with the critical point of this functional. So we can get the compact. So we can get a compactness. So we can prove this result. Okay. Finally, I'll show you some one application of our method. In this paper, Ding Yanheng and Tanaka, they consider this equation. Actually, I simped this equation. I simplify the equation in this paper. In this paper, they wrote here is ax, not 1, but they have the same. Maybe I wrote like this is easy to understand. Okay. Here Vx is non-negative and omega is a non-empty bounded, has a smooth boundary, and omega consists of key components. Intersection of closure of omega I and closure of omega j is empty. For example, this is integral v 这个东西。Okay. In this paper they didn't they want to get some special solution, not just a solution. They want to get a sorry. In order to study this equation, the difficulty is lack of compactness, because as I said before, H1 of Rn into LQ of Rn is not this embedding is not compact. Okay, and in this paper, Ding and Tanaka want to get some special solution, not just a solution. So they consider this problem on a special site by a process analysis and of the deformation flow. They consider the they looked for a solution on a special site by using deformation flow. In order to overcome the the lackness of the compact embedding, the lack of compact embedding, they used the panelization method due to Pino and Felmer. So we consider this equation minus, so here is a logarithmic nonlinear term. Compare these two equations. Here is 1, here is no 1, because u square times the log u square. The derivative of u square log u square has 2 terms, so we should delete 1. Our result is later I'll show our method. Suppose that V satisfies V1 and V2, then for any non-empty subside gamma of this side, for example, gamma is 1 and 2. There exists lambda star is bigger than 0, such that for all lambda is bigger than or equal to lambda star, problem P lambda has a positive solution U lambda. Okay, this is the existence of solution. Moreover, the family U lambda has the following properties. For any sequence, lambda goes to infinity. we can extract a subsequence lambda ni such that u lambda ni converges strongly in H1 of Rn to a function u, which satisfies u of x equals 0 for x is not omega gamma, and the restriction is a least energy solution of this equation. This is the ground state solution. For example, gamma is 1, 2. They can get a solution. And if lambda is big enough, u lambda almost equals 0 if x is not does not belong to omega 1 and omega 2. That is, if x belongs to omega 3 to 4 up to omega k, u lambda almost equals 0. We should notice almost equals 0. It's in norm. It's not in functional value. If lambda is big enough, u lambda almost equals the ground state solution of this equation in omega 1 and omega 2. It's also in norm, not in functional value. Okay, so this is maybe you can I don't know if you understand the for example, here is omega 1, omega 2. If lambda is bigger enough, u lambda has a value omega 1 and omega 2 almost equals 0 on omega gamma, outside omega gamma. So we call it a multiple bump solution. Okay. In order to research this problem, this equation, Ding and Tanaka used the panelization method to overcome the lack of compactness. Because of our paper in CVPTE, we also can use this method. We just use this method for F2. We can see F2 prime as a nonlinear term. But in order to look for a special solution, Ding and Tanaka is looking to look for a solution on a special site by using deformation flow. The function of this equation corresponding to is C1, but for our problem is not. So we can consider a modified problem in a bounded ball. We used this method before. Okay. So we should do some L infinity estimate in order to prove the solution of the modified problem is a solution of the original problem. So if u lambda is a family solution of positive of the modified problem with this, and we can get this L infinity estimation. So we looked for the solution on this special site. This assumption can assure. Let's pay attention to this. If mu is small enough, yeah, u lambda is equal to 0 in this norm, in this space. If mu is small enough, so we have this L infinity estimation. So we can prove the solution of the modified problem is a solution of original problem. This this condition can assure we can get a multi-bump solution, not just a solution, not just solution. Okay. Finally, I would like to see some difference between our proof with the proof of this paper. Because we consider a modified problem in a bounded ball, BR. So in our problem, we have to face two parameters, lambda and R. So we have to do some estimates for R and lambda big enough uniformly. In Ding and Tanak's paper, they just consider lambda. In our paper, we should consider R, lambda and R. For some results, it must be uniformly. Okay. Thank you very much. That's all my talk. Okay, thank you.
Thank you, Professor. Oh, any questions?
Maybe you guys cannot understand my English.
Nice. Yes. No questions?
大概你能
嗯
OK，
好像没什么问题。
OK，我不知道我大概说清楚了吗
说得好，说得挺清楚的。
OK，Thank
都
you，Jules，Thank you。
Thank you，
啊，
是卡鲁斯好像进来啊，他等一会儿可能要跟你聊两句。
哦，好吧。
então
OK，
thank you，
OK，
OK，
Thank you very much. I hope everyone can understand my English. Okay. I also hope to make some cooperation with you guys. If you are interested in my research result, maybe we can do some cooperation. Thank you very much.
Então, vamos terminar aqui. E aí, semana que vem tem outro,
Okay.
tá? Professor Tu. Só que o horário é 4 horas da tarde, tá?你等一会儿提出来啊，他这个卡路斯可能要跟你说两句。
OK。我听过他一个报告，他英语蛮好的。就上一次 OK。